write down our familiar situation, which is that U, so strike. So higher derivatives and higher partial derivatives. Let's write down the situation. U is an open set in Rm, and f is a function from U to Rm. So let us say f has component functions. So any point, let us say x, goes to f1x up to fnx. Okay, I should also start recording. Let me just do that.
Recording in progress.
Okay, so we are in the standard situation where I have a function defined on an open set of Rm to some Rn, and we want to see what it means to take higher derivatives of this function and also higher partial derivatives. So this f will have n component functions, f1 up to fn. So the first slot in you have the function, you have the number f1 of x, where x is your input, and so on. Let me just write here, f has component functions f1 up to fn. With respect to the standard So philosophical point here, it is tremendous that we can coordinatize the Euclidean space and do geometry by means of numbers and then doing calculations with numbers. However, you see, if you go back to Euclidean geometry, then one can do geometry without any recourse to numbers. So putting coordinates just gives me an address system, but I can use different address systems. So this idea that geometry is something that is, that there is something intrinsic about the geometry that is independent of the coordinates is always useful to keep at the back of mind. And one of the things in linear algebra, one of the lessons in linear algebra that you learned is that sometimes it really pays to think of a vector independent of the coordinates of that vector. Even if you're working in Rn, sometimes you can postpone the choice of basis until you can choose a good basis to describe the situation at hand. I mean, one reason to say this is that we saw that the derivative of f is really a linear map. I can think of the matrix of this linear map, but a vector exists independent of its coordinates. And likewise, a linear map can be thought of without there being a matrix, without making a commitment as to which basis I am choosing. So, all right. So what is the derivative? So f prime of A, or the derivative of f at a point A, is, we know exactly what it is a linear map from Rm to Rn, such that a certain limit is 0, but I will not write that down, i.e. is an element of the space of all linear maps from Rm to Rn. Okay. Therefore, then we have then f prime itself becomes a map. F prime, the d of f, which is a map from where? For every point in U, just see what we have written in the first bullet point. For every point in U, I get a linear map from Rm to Rn. So, which is a vector space of dimension Mn. So, I can consider continuity of f prime. It's a map between something, it's a map from a vector space to, it's a map from a metric space, a subset of this Euclidean space, to another, to some Euclidean space, right? So I can apply all my concepts of topology over here. So if f prime is continuous, we call f a C1 function. And what did we see? We saw that f is C1 if and only if, what happens quickly?
All of its partial derivatives are continuous.
Right, all the partial derivatives exist and they have to be continuous. All del fi by del xj are exist and continuous on. By the way, each del fi by del xj is what kind of function? From where to where?
R to
R. No.
U to R.
From U to R, correct? So all of these are continuous functions on U. So I can consider continuity, but here is the thing. I can also consider differentiability because it is a function. Again, it is a function from a subset of the Euclidean space and an open subset to a vector space. Prime at any a in U. So if f prime has a derivative, of f prime at A, which we can call f double prime of A, or I can call it d, maybe d2 of f. What kind of gadget is this? And we saw this last time. Is a linear map from where to where? Again, I just have to, so remember where, what f prime, so let's just look above. How do I take the derivative of any function? I just look at what it is from to what it is, and it's the map between linear spaces of that dimension. So again, this is a linear map from, so linear map from, again, Rm, because f prime is a map from U, but now it is going to be from where to where? Again, this is going to be from the same vector space as the target of my original map. So this is the derivative of f prime at any, right? So again, is a linear map. Let me write down f double prime of. Okay, very good.
Sir,
So what are the yes, go ahead,
sir,
please.
I had a question regarding the first thing we were talking about bases. This characterization of C1 functions, I guess it would
Right.
work for any orthonormal basis.
That's a very good question. I want you to think about it. So,
Okay, sir. Yeah.
so even the meaning of this question has to be made a little clear. So, I mean, let me just say this for everyone. So the question that he asked was that the characterization of C1 was in terms of a specific way of representing F, right? Namely the component functions f1, f2 up to fn used a certain basis. I used a certain coordinate system, and you could say that I used a coordinate system even for you. So the question is, could I use some other kind of coordinate system, and will the characterization stay valid? What would it look like? The question is not completely precise. It's still slightly vague, but the idea, I hope, is clear. I want everyone to think about this question. But all right, so let's look at the double derivative. The question is now, so if I want to describe this double derivative again at a point, okay, I'm not varying the point yet. But if I want to describe this double derivative in terms of its coordinates, then what would it look like? So we have to understand the meaning of this question first. So remember, f itself had components f1 up to fn. Then what were the components of the function f prime? How many components does the function f prime have? So look at the second bullet point. How many components does the function f prime have if it's defined on all of you? M times n, right? And in fact, what are those component functions? Well, okay, so if this is the case, then you have to ask me components with respect to which basis. So which basis am I choosing for L, Rm, Rn?
So the standard basis for r to the power n.
Well, I have to use standard basis for both r to the power m and r to the power n. So these are elementary matrices, correct? One in a certain slot of the matrix and zero everywhere else. Now, excuse me. So, yeah, so what are the component functions? What are the component functions of this map f prime?
If we take standard basis for Rm and Rn, they're exactly del fi by del x2.
Exactly. So you see the component functions of of f prime as a map from U to L are precisely the partial derivatives del fi by del xj at various, evaluated at various points. And we should write down I going from 1 up to n and j going from 1 up to n. As such, what will be the components of f double prime of p? So, so getting ahead a little bit. So you see f double prime, so the matrix of f double prime of A with respect to standard basis of Rm and LRM. Which numbers? And let's just go back. What did we say? For any function f, in fact, if you want, you think of this function f as g, right? What did we say? That if if this function g has components g1 up to gn, then the matrix of g prime of A consists of just the partial derivatives of all the component functions with respect to the directions in my source set. So I am applying the same thing now for the function f prime. So what are the components of f prime? The components of f prime are simply the partial derivatives of each fi with respect to xj. Therefore, what will be the matrix of f double prime?
So the partial derivatives of each of these component functions
Right.
with respect to the basis.
And so, right. So, and that's a general description. So what we have to do is we have to take partial derivatives with respect to all the xi's of each one of the component functions. But the component functions here are themselves partial derivatives of f. So what we are going to get is and let me write it in this. Let me write it in this way. The operator del by the operation del by del xj applied to fi. That is going to give me a function, remember. And then a function from, remember, a function from u to real numbers. And I'm going to, it's a function from u to real numbers. So I can again take partial derivative of that with respect to any direction I like. And when I do it for each direction, and when, so this is what are going to give me the components of the double derivative function. But of course, this is going to be evaluated at A. So let's see. And if you really want, what this is that it's this whole thing evaluated at A. Okay. All right. So any questions so far?
Sir, I had two unrelated questions that I actually wanted to ask at the start of the class, but I joined a little late.
Okay, maybe you can just state those questions and then let's see if we can do it now. Or
I said no, not like math questions, just like some other stuff. One thing is
so
that,
I think I think in that case maybe we will wait until after the class to discuss.
Sure.
Thanks. Okay. All right. So it's going to consist of these numbers, and we also get assuming f double prime A exists. Okay. So before that, so note that if the total derivative of any function exists at a point, then all partial derivatives exist at that point, right? So, say if f double prime of A exists, nothing new is happening. We are just applying whatever earlier results that we had proved for f to the function f prime. The moment it is differentiable, all of that comes in, right? These are guaranteed to exist. Now, let us go further and say f double prime as a function. If f double prime A exists at each A in U, then I have function f double prime. And now this is a function from where to where? F double prime from U to where? And it is easy because A goes to f double prime of A. So what kind of animal is f double prime of A? Let's just look. F double prime of A is a map that takes in an input from Rm and produces a linear map from Rm to Rn. So This is in the space of linear maps from Rm to the space of linear maps from Rm to Rm. And I asked you to think about what this space is. So this is also the, not also, let me just say equivalent to, not having. So because I'm talking about a space. So anyone, quickly the answer to this? This space is equivalent to?
Sir, Rm square.
Yes. All right. So what you want to say is, so space of, this is just an aside. You want to say Rm square, right? So let me, not really. So this is really equivalent to the set of maps from Rm cross Rm to Rn. But what kind of maps?
I think bilinear, sir.
Yes. So this is just an aside. But anyway, so now the question is, we can just sort of keep playing this game again and again up to higher levels. So now we have said that suppose f double prime of a exists at each point, that means the function is doubly differentiable. Then I have this map. The target space now is something of dimension what? The target space is of dimension m square n now. Yes. Anyway, it's a vector space. So this map now has m square times n components. I can consider the differentiability, I can consider the continuity of this map, I can consider the differentiability of this map, and so on. Let's just look at continuity. So we say f double prime, again it's a parallel discussion. So let's look up here. So let me just number these points too. So now the analog of 3 is that f is called a C1 function if the derivative of f exists on this open set and is continuous, and that is characterized by the continuity of all the partial derivatives. In exactly the same way, I say that f is of type C2. So this is the definition if f double prime is continuous on all of you. And this will happen if and only if so this is just the definition. So what is the characterization? Remember, we had a characterization for C1 functions. The exact same thing is going to apply here. Continuous on U. But what does f double prime being continuous on U have to say? What does that mean? That simply means that the derivative of f prime is continuous on U. But the derivative of any function being continuous is equivalent to all the partial derivatives of that being continuous. So what are all these partial derivatives of all the components?
The mixed partial derivative.
Yeah. So well, then it didn't. Okay, so I haven't really used the word what mixed partial derivatives. So what we mean is just double partial derivatives, right? Which is to say del by del xk of del by del x. What did we have? J of fi. All of these are continuous functions. From where to where? From where to where?
U to R.
Exactly. And so on. So we have the class C2, we have the class C3, and then we continue in this fashion. What we want to, so all of this was really just getting used to semantics, okay, nothing more than that. But what we want to now closely examine is these double partial derivatives. Okay. And so examples. Check that for many functions. See, I'm trying to make a mathematical statement, but so let me make it. Commonly used functions, including polynomials, sine, cosine, exponential functions, right? So what I mean is these are polynomials, etc., of multiple variables, and you are doing the algebra of them, which is, add, subtract, multiply, compose. You have del by del x, k of del by del x, L of f is equal to del by del x, L of del by del x, k of f. Of course, this is interesting when k and L are different, because if k and L are the same, then you see we are not really saying anything. Those two sides are. You can see this by examples. So the question is, does it happen always? And the answer is no. But there is a sufficient condition for this to happen, which we want to prove. So that is our sort of main job today, first main job. So under which conditions? So we are going to give a sufficient answer to this question. So let's state this. So one answer. True if f is C2. Again, remember what C2 means? That means on the entire open set, it is differentiable. The derivative is also differentiable. That is, the second derivative exists at each point. And the second derivative is a continuous function. So we can prove something a little more general. So let us sort of set this up. So lemma. So we will consider the two variable situation. And that goes about as follows. So let U be open in R2 and F is a map, just a real value function. So you can say, well, we want to prove this in general. So why are we doing this? Well, the question is that we are going to be dealing with only two directions at a time. So it is enough to hold all the other directions, whatever is happening, constant. So it is enough to deal with two variables. And the thing is, as we have seen multiple times, to check continuity, to calculate limits, to calculate derivatives of a function that has many components, you can work component by component. So it is enough to deal with just a real value function. So what is the lemma going to say? We have to set up a little bit of terminology. So let us say that A comma B is in U. And in fact, So we want to say, I'm following the completely standard terminology. This is taken straight from Rudin's book, and Pramath has done also it exactly the same way. So you can, so this is going to be the rectangle. Okay, let's write this as A plus H cross B plus K. This is the set in, so this is a closed rectangle. So we'll just draw this. So this is A, and this is A plus H. Sorry, A comma B and A plus H comma B. And then in this direction, you go up to A, B plus K. And so this other one is going to be A plus H, B plus K. That's what the set is. So we are going to be studying variation of this function within this rectangle and prove something nice and simple really by application of the mean value theorem twice. All right, so let's set this up. So by taking remember, this is an open set. So if A comma B is in U, then I can put a small circle, small rectangle, small square. You know, it's by topologies are all the same. So I can put a small rectangle around this. So assume that this is the case, that the entire rectangle is contained in U. So I can evaluate the function. So I define. We are still in the let phase. Okay, we still have not made the statement of the theorem. So we define. Now, what's the notation? Delta F. This is the standard kind of thing that you will see. Minus A, B plus K, A plus H, B plus F of A. So notice that this is also the same thing as F of A plus H, B plus K. And we can pair up the terms in two different ways over here. Then, okay, so which way do I want to do this? Okay, minus F of A plus H, B minus F of A, B plus K minus F of A. Correct? Now just think about it a little bit. If I divide this whole thing, so this is going to be, so in view of what we are, I'm just trying to set up what is coming. If I divide both of these things by a certain, what should I divide both of these things by? And then take the limit as that things approaches zero to relate this to some kinds of derivatives. Okay, look at the term in the second, brackets. If I divide that by K and take the limit as K approaches zero, then what do I get?
A partial derivative.
Partial derivative of F with respect to which variable at what point?
With respect to our second variable, first at A plus H and then at A.
Right, exactly. So you see, both of these are going to be partial derivatives. So for future, let us just note this. By the way, we are still in the statement of the lemma, but so let me parenthetically note. limit as k approaches 0 of delta fq by k is equal to what? Del by del. And let's just call the variables x and y. Okay, the first variable x, the second variable y. So what is it going to be? Del by del what? Of del f by del what? Y. At what point? Come on, this is easy. I'm just setting this up because you're going to need this later on.
So which ones are you calling X and Y? Sorry.
I'm sorry, what?
Which ones are you calling X and Y?
So x is first variable, so and y is the second variable. So first variable equal to x, second variable equal to y. So it's in the second slot that I'm allowing this variation, right? That k is approaching 0. So this is del f by del y of what? At what point?
A plus HB.
A plus h comma b. And in the second one, I'm going to have del f by del y you have at the point a comma b. Very good. And just going ahead further, this is also, if I then divide this quantity by h and then take the limit as h approaches 0, what will I get? If it exists, right? If these derivatives exist. And then therefore limit as h approaches 0 of this above thing, the limit as k approaches 0 of delta fq divided by k. What will that be? Oh, sorry. Sorry. So what is missing over here?
So we didn't divide by k.
Yeah, so I have to divide this whole thing by k. Divide this whole thing by h. What will that equal?
So the partial derivative with respect to the first variable.
Yeah, the partial derivative with respect to x of what?
A comma b, at a comma b.
At a comma b, but of what?
Of
Not
the partial
of,
derivative with
yeah,
respect
right?
to
Of whatever difference I have. It's the difference between values of the function del f by del y, right? So this is of del by del y of f. So this whole thing at a comma b. And this is exactly the quantity that I want to analyze, right? I want to analyze the second partial derivative, and I want to see whether, second partial derivatives of f, and I want to examine whether I first take partial with respect to y and then x, and the other way around. Then I want to compare both of these. So that's why this whole thing is going to be useful. So let's, so this is all really in parentheses. So let me just put a box around this. Let's continue with the lemma. And the lemma is going to say something about this quantity. Then there exists a point somewhere in that rectangle S and T in rectangle. Sorry, it not just in the interior of the rectangle. Rectangle QHK such that and hopefully the shape of this, what we have over here, H times k times okay. So all of this is really evaluated, right? At s comma t. All right. So did I make a mistake over here? Notice that up there I have written del x, del by del x, and then del by del y. Here I am doing it the other way around. And for ease of notation, by the way, so let me just say this is h times k times d21 of f evaluated at s comma t. That 2 stands for for the partial derivative with respect to the second variable, and 1 is partial derivative with respect to the first variable. So this is just notation. Okay. Of course, assuming that this partial derivative exists. Okay. All right. So let's prove this, and the proof of this is just going to be, just mean value theorem. So let's draw a picture. I'm first going to see. I'm going to vary one direction at a time over here. So let's define u of x is equal to f of x b plus k minus f of x b. So in terms of the picture, this is what I have. This is AB, that is a plus hb, and in the first variable I'm taking an arbitrary point x. And everywhere when I go in the upward direction, so this is a plus h, b plus k. So let's scrunched over there. I mean, you see what I'm saying. Let me not label it once again. The important thing is that this is what. So this is x comma b plus k. Okay, very well. So then, in terms of what is delta fq in terms of u? Just look.
U of A plus H minus U of A.
Right. So if I take u of a plus h, u of a plus h. So if you look in the definition of, let me just make this smaller. Here. U of a is, so if you look at the definition of delta, u of a plus h gives me which terms? The first two terms, correct? Sorry, not the first two terms. The first term and the third term. Yeah. So what should I do? What else should I do in order to get delta of f? U of
A.
So just look over here. In fact, if you see the second expression defining delta, then that is better. Notice that in the definition of u, the first slot is kept fixed. It is at x, and the second slot changes between b plus k and b. That's exactly what I have on the second line. In the first square brackets, I have the quantity u of a plus h. And what is the quantity in the second square brackets?
U of A.
U of a. So good. Now I play the usual game. I apply the mean value theorem to this. So u is okay. I should really have written the Okay, so we will just say that we have the requisite differentiability for f. So by mean value theorem, what do I get? There exists, we have some value s in, okay, so h is now very, all right, so these are between a and a plus h. So I have some s between a and a plus h, such that what happens? Delta fq is equal to what? Or rather u of a plus h minus u of a plus h minus u of a. By the mean value theorem, what do I get? U prime of something, right? U prime of s. This is just a single variable function times what?
H.
Times h. Just by one variable mean value theorem. But what is u prime of s?
F dash of S, comma B plus K minus F
Yeah.
dash of S.
So, okay, so this is h. So just 1 second. So u prime of. Sorry, just give me one moment. Okay, I have to do something. Just give me a moment.
Recording stopped.
Just for a couple of minutes. Just please think about this for a moment.
Recording in progress.
Okay, so we have obtained h u prime of s. So let's go further. Now let's look at u. What does it mean to take the derivative of u as a function of x? Remember, u is just a difference between f of xb plus k and f of xb. So what does it mean to take the derivative of u with respect to x? Well, it's a difference between two things. So that means I have to take the derivative of the first term regarded as a function of x, and I have to take the derivative of the second term regarded as a function of x and subtract. So what are these two things? So this is h times, what is u prime? What is the first term? You see, the first term is f of xb plus k, right? And I have to take the derivative of that I have to take the derivative of that quantity as x varies, and I have to take that derivative at s. In other words, what is that thing? It is just del f by del x. But at which point?
S comma B.
S comma
B plus
actually
K,
b
sorry.
plus k, right?
Yeah.
Okay, very good. And in exactly the same way, the second term is del f by del x at
S comma B.
s comma b. Okay, very good. Now what do I do? You see, now if you look at this difference in the parentheses, it is again value of a certain function at 2 points and subtract it. So I can apply the mean value theorem to this. Applying MVT to the function del f by del x. But now exactly. You tell me precisely which function I'm applying this mean value theorem to. Single variable mean value theorem. So I'm applying it to the function del f by del x evaluated at s comma variable on the interval. Which interval?
B comma B plus.
B comma B plus K. So what do I get? H times
K into the y.
H times K times del by del. Okay. But I have to, but okay, but it's the So I'm taking the derivative of this function with respect to the variable which is in the second slot. That means the mean value theorem will give me something such that will give me a point. So I get t in b to b plus k such that this happens. So what do I get? Del by h times k times some value t such that the derivative of the function that I have written at that point is equal to k times the difference in the square brackets. So what do I write? H times k times what?
Del y of del
Of del f by del x. At
at
the point,
f comma t.
but look up, that's exactly what we said we wanted. All right. So what did we need for this to work? What did we need? We needed to apply the mean value theorem twice. That means that the function f regarded as a function in the first variable. See this function u, I needed to apply mean value theorem to that. That is a function of x. That means that on every vertical line segment, I need to be able to apply. Sorry, just 1 second. I'm a bit confused over here. So what is the hypothesis that we require?
So we need both u and the new function and like del f del x at s to
Right. So both of those functions must be continuous on the requisite interval. I'm just trying to interpret this in terms of the original function f. What does that mean?
So then f is differentiable on both the first variable and the second variable.
Right. So sir, so of course, if the total derivative f exists, then that is perfectly good. But it is enough for us to have that the function is differentiable on every vertical segment, right? And the partial derivative with respect to x is also sorry. Yeah. So see, del f by del x has to be del f by del x has to be a differentiable function, has to be continuous on the closed interval and differentiable on the open interval. So strictly speaking, this needs to happen only when x is equal to s, only on that vertical line. But I don't really know in advance what s I need, so it really needs to happen on every single one. So okay, so I'm getting a bit confused over here. So let me just say, so figure out the exact hypothesis required for.
So we need f to be differentiable on the first variable, and we need del f del x to be differentiable del f del x, and for each, like if you fix the first variable of del f del x, then all the resulting functions have to also be differentiable.
Right. So in other words, del f by del x has to be on every vertical line segment. The function del f by del x has to be differentiable.
Yeah.
Right. Yeah, and what does it mean to say that the function u? See, the function u is the one that I want to apply the mean value theorem to, right? So what does it mean to say that the function u is differentiable? But maybe we have sufficient conditions. So
So technically we just need differentiability of like f on each of the on like the lowest
The
horizontal line and the uppermost horizontal.
right. Okay. Um, yeah, so certainly, so okay, so basically you're saying that in the lowest horizontal segment and the highest horizontal segment, if I have differentiability on that, will that work? Sorry, I got confused over here. So certainly it is enough to say, okay, it is, yeah, it is enough to have del f by del x, del f by del y, and del by del y of del f by del x exist. This is correct, right? Because those were the only derivatives that we used over here. Yeah. So be that as it may, but I hope you understand the second statement, that these were the only partial derivatives. So if both partial derivatives exist and the partial derivative with respect to y of the partial derivative with respect to f, if they exist, then this proof is perfectly all right, because I can use mean value theorem wherever I want. Okay, so with this lemma in hand, let's actually prove the result. So theorem. And now we'll be careful. Suppose for above f, d21, which is equal to del by del y of del by del x. Is continuous at a comma b. So this is a bit stronger. Not only are we saying that the mixed partial derivatives are equal, just the existence of one is enough to ensure the existence of the other, and then the two have to be. Then d1 to f is equal to del by del x of del by del y of f exists, of course, at AB. So maybe I should really just say d1 to FAB equal to this at AB exists, and the two things are equal. So d21 f AB is equal to d1 to f. So I'm just using this notation d12 and d2f's just for brevity. So let's prove this theorem. And as usual, there is an epsilon delta argument. So the continuity of something in the multivariable situation, it says something very nice. It says that not only are you continuous by coming in any particular fixed direction, but really for every epsilon, there exists a delta such that if you are within the delta distance in any direction around the desired point, then applying the function lands you within distance epsilon. So let's write this down. So let epsilon greater than 0. Then continuity of this D21 means the following. Is that the value of that as soon as you are within distance delta in any direction from A comma B, the value of the double derivative cannot deviate by more than epsilon. So means there exists delta greater than 0 such that for all H and K, the function that I'm claiming to be continuous, which is D1 of F, evaluated at any point D21F at xy and D at A comma B, their difference is going to be X for all X and Y where in this rectangle Q, what do we call this? QHK, no? QHK. Okay. So pause here for a moment and understand. So what is happening? So this is this set, whatever is the set U. Now here is the point. The function whose continuity I am considering is del by del y of del by del x of f, which I have written as D21 of f. Now here is the point A comma B. What I'm saying is that given any epsilon, I can find the ball around this point such that for every point within that ball, the value of the function D21 does not deviate by more than epsilon. But instead of taking a ball in the Euclidean space, I might as well take a rectangle, right? Because you see, inside any ball, I can fix a rectangle. Okay, so any questions on this? This is really just writing down the meaning of continuity, nothing else. All right. So from now here, it's just a matter of following our nose, as it were, and see what's going on. Now, notice that I'm already given that D21 exists, that is del by del y of del by del x of f exists everywhere and is continuous. I want to show that D12 exists and is actually equal. So how do I calculate D12? And let's just go back and take a look over here. D12 means I first calculate the derivative with respect to y, that's the 2, and then calculate the derivative with respect to x. So this calculation which is given in this green rectangle is exactly the thing that is going to be useful for us. Okay. So let's write this down. The second limit that I'm calculating is really the, so what I should do is I should take this quantity delta FQ, the 4-term expression, and divide that by H and K. And then take the limits as H and K approach 0 in the appropriate order. So first I take the limit as K approaches 0, and then I take the limit as H approaches 0. All right, so let's do this. So, yeah, D21 of fxy. So this means that so take H and K as above, and use the lemma to find S and T, such that, what did the lemma tell us? Delta FQ, that 4-term quantity, is equal to H times K times D21 of FST. Right? Let's look at the statement of the lemma. H times K of, so see, this is what the lemma is saying. All right, so let us just substitute this quantity over here. I'm going to substitute by writing delta FQ by HK and then estimate. Oops. Divided by H times K. And then the second one will now just carry along for. And now I play the game as above. So let's look at the calculation. The calculation in the green rectangle. I'm first going to divide by K and take the limit, and then going to divide by, and then take the 1 by H and take the limit. Remember, I have both K, H and K available in the denominator. So what does this give? So this is 1 by H and the quantity of A plus H, B plus K minus F of A plus H B divided by K minus F of okay, so sorry, we lost the screen. We just of what do we get now? So A plus H I have kept fixed and taken B plus K and B in the second slot. So now we'll take A, B plus K minus F of A, B divided by K. Oh, okay, sorry. This is so all of this minus D to 1 F A B. All of this, sorry. So this is, so IE, this is less than epsilon. What do I do now? See, this quantity is less than epsilon. So I can take the limit as, K approaches 0 to get what? You see, some quantity. Okay, yeah, I mean, this is standard analysis one. So you tell me now what happens. You see this term over here. Sorry, the parenthesis is in the wrong place here. this quantity without the h, this quantity, if I take its limit, you see this quantity minus the second one, think of it as a fixed number. So let's say the next number is 5, for example. So some quantity minus 5, their difference is at most epsilon. Now the quantity that is in the first place, that is varying. If I take the limit of that quantity, then the difference of the limit from 5 is also going to be at most epsilon, right? At most what will happen is that the less than epsilon sign will change to less than or equal to epsilon, but that is okay, no? So what happens if I take the limit? What is the limit of the quantity that is in the parentheses as k approaches 0? Come on.
Del f by del y.
Right.
First at a plus h comma b, and then at a comma b.
Right. So a plus h comma b minus del f by del y of a comma b. This quantity, and of course minus d21a d21f a comma b goes along further, right? So what do I get to say now? This need not be less than epsilon, but after taking the limit, this is less than or equal to epsilon. Okay. Now what do? I take limit as h approaches 0 to get what?
Sir, don't we need some assumptions for the first partial derivatives in the statement?
Exactly. Now that's a very good point. The point though is that okay, so let's back up and see. All right. So we have the first quantity. Notice that this is true for every x and y that is taken within this rectangle, right? So remember, I fixed an epsilon. Epsilon was arbitrary. Given that epsilon, I found a delta, and I found that for all values of x and y within this rectangle, I'm having such a thing, right? So in fact, what this is saying is that so you're absolutely right. So I need to formulate this. This in fact shows off what does it mean to show? What does it mean to say that some quantity has a limit? It means that given any epsilon, there is a delta such that blah blah blah, etc. The difference whenever you take whenever you are evaluating your function, the difference between the function values in the prescribed region is less than epsilon. We are supposed to guarantee such a delta, right? So what is the limit of that quantity in the exists? And so in other words, what happens? D12 of f at AB exists. So this is in del by del x of del by del y of f at A comma B exists and is equal to D21 of f A comma B. Oops, my goodness, we are way out of time. I did not realize that, so we should stop.
Recording stopped.
Yeah, sorry. So this was a bit discombobulated at the end. If there are any questions, then I can address it now. This may seem a little bloody here, but it really is just a question of setting up the terminology. And what I want to say is that the way we are doing it is that everything is really about this rectangle. In one way of doing it, we first take the derivative in one direction and then in another direction, and then we switch the order. But the continuity of the derivative of one of those mixed partial derivatives allows me to switch the order and show that what I get by switching the order is really the same. This is what is achieved by this small lemma using the mean value theorem. And really, all the action that is happening is that if you look at this quantity delta FQ, I can arrange the two negative terms in two different ways. That's all that is happening. When we arrange it in the way that I have done over here, then that corresponds to taking the derivatives in one order. And if I switch the order of the terms, then that corresponds to taking the derivatives in the other order. But really nothing much is going on.
So this seems like we're getting a lot out of something. Like we're not starting with much, but we're getting a lot.
But okay, so what is the key hypothesis over here? The key hypothesis over here is that one of those mixed partial derivatives is continuous on the entire plane. And that means that no matter which direction you go to, there is a uniform delta that will work for a given epsilon, no matter which direction you go in.
Oh, so did we assume that it's continuous on?
Yeah, so you see the hypothesis for the theorem. D21 of f is supposed to be continuous at that point.
Right.
So that is what is being used. So you see, what is happening is that therefore I can choose h and k both less than delta, such that this delta will work simultaneously for both of them. You see, this x and y could be really anything in the rectangle.
I think I see. It's sort of that. Perhaps it's kind of that. The directions don't really talk to each other, and so the continuity lets us choose something that works for both simultaneously, and so we can just switch it around in some vague sense.
Well, no, I mean, I'm not really sure how to respond to that.
So I had a couple of things to say. So the first thing is we get that so can you scroll down a little bit?
Okay, so where should I go?
Just a little bit. Yeah, so that you said that we take the limit as h tends to 0, and we claim that this limit exists because this value, as h gets smaller, closer and closer to 0, it's always epsilon away from d to 1.
Right, okay.
So the existence, why, not exactly sure why it should exist.
Okay, all right. Okay, all right. So let's, what does it mean to say? So basically this is what you want to spell out. Right? Why is this true?
Yeah, why should it exist?
Okay. So let's look at that. So let's look at that quantity, the one that is in the curly braces. This inequality is true for which values of h?
I mean, for all sufficient values of h sufficiently close to 0.
Right. So you see, this is going to be true for, so I hope I wrote, yeah. So you see, for all h and k that are within distance delta. Yeah. So in fact, let me draw this picture better here. See, for any, when I fix an h and k, then I'm going to get a rectangle. But you see, h and k could also be negative. So this rectangle could go in any direction. Yeah. So really there is more than one rectangle over here. The first thing that I have is I first have this delta in each direction, right?
Yeah.
Maximum of h and k less than delta. That means I'm allowed to go delta in each direction.
Sure.
So this is 2 delta. And now, so this is a comma b. But this point could be anywhere in that, and that is a plus h, b plus k. All right. Now for any such h and k, whatever inequalities that I'm writing down before taking the limit, they're valid for any such h and k. Right? Okay, so now let's go with the inequalities. So the inequalities are true. The first one, before taking the limit, nothing is happening. Now, when I take the limit as k approaches 0, I get this inequality. Less than or equal to epsilon, doesn't matter. But this inequality is true for every single h, right?
Yeah.
Every single h that is less than delta.
Yes.
But what does it mean to say that the function del f by del y at a fixed, has a derivative at the point a comma b?
The limit
Right.
exists.
There is a derivative in the x direction at the point a comma b. What does it mean to say that? It means precisely to write this difference quotient that we have written.
Oh, right.
So that
Yeah.
and we have to show that this quantity approaches a fixed number, right?
Got it. Got it.
But which number? But I'm just now trying to, but to show that a limit of a certain quantity is 5 is really the same thing as showing that the limit of that quantity minus 5 is 0. And that's exactly what we have written.
Makes
So let me just say this shows that. So this is just using not even formulation. It's just a definition. Strictly speaking, I have less than or equal to epsilon, but rather than less than epsilon, but it's neither here nor there. Just use whatever epsilon by 2, 2 epsilon or something like that.
Sir, should D21 and D12 exist in an open interval?
No, say that again, please.
Should D21 and D12 of f exist in an open interval?
So it will be a consequence of this. So notice the hypothesis here. We wanted to say that so D21 is continuous, right? That was used right off the bat. That means that this double partial derivative certainly has to exist in a neighborhood around a comma b. Yeah. Without that, we can't get started. Correct? So a priori, we are not even assuming that D12 exists at a comma b, or for that matter, anywhere. But the hypothesis is saying that D21, that is del by del y of del by del x, that of f, that function exists in a neighborhood around the given point and is continuous. So after having proved this result, I can apply it at any point in this neighborhood and conclude that the other way double partial derivative also has to exist.
Sir, just a thing.
Yeah,
I
but
found
so but just one more thing.
Sure,
So
sure.
what else is required? Um, yeah, but you see, we are writing down del f by del y. So that also has to exist. That means that so we should really add this. So I think so the blanket assumption, maybe this is what we should write this everywhere. Blanket assumption. Yeah, so where did I write this down? So this, let me just. How about this? And then we are perfectly good. Because the first partial derivative I can talk about everywhere. In any case, notice that for del by del y of del f by del x to exist, I first have to have the del by del x of f exist everywhere, right? So the continuity of D to 1 in particular is saying that del by del x exists everywhere. And then del by del y of that exists everywhere and is continuous. Now, the point is del f by del y also exists, because you see, I'm writing that down in this expression over here. I'm writing this down. I'm assuming that this limit exists. No, remember when I took the limit as k approaches 0, I wrote del f by del y. That means that it has to exist. So I should just state this as a. Let me state it as a. Suppose for above f, this and how about this? I think now this is. So that is now a complete statement. The first partials exist, and the stated second partial derivative is continuous. That means it also has to exist. Okay, any other questions?
Yes, so just a thing. I think Gautam was saying that, like, and in general, the only reason why this like should be true is because D21 and D12 are sort of like refined. Like they're like limits of the same differential quantity. Like,
Right, but you see, this is one very big thing in analysis. If you want to take the limit, and if you're taking two limits, see, the limits are being taken as h approaches 0 and as k approaches 0, right?
yeah,
So this question is really about, can I interchange the order of limits?
yeah, exactly.
And these I mean, this is huge in analysis, right? You all the time you worry about these kinds of things. Can I differentiate under an integral sign, right? Changing the order of operations and when is it valid that I get the same result is a very basic question in analysis. And it does not always work, right? I mean, you should know some basic examples. Like, for example, if you take like for sequences, I hope you saw this in analysis one, right? You take the sequence all zeros, like a rectangular array, basically, where the lower part is all ones and the upper part is all zeros. And I don't care about the diagonal. The limit of the rows, the limit of each row is 0. And the limit of those zeros is therefore 0. But the limit of all columns is 1, and the limit of those limits is 1, right? This is a standard first example in analysis to one of the first examples. So changing the order of operations is a big deal. And we just showed here that it's possible because of continuity. Because of continuity, somehow those things are held together. Notice also one other thing. So I'm now making a different point, sort of showing where linear algebra is going to come into the play. So for functions, so in good conditions, if I calculate the double derivative, the matrix of the double derivative, let us say I have a single real valued function. So f itself does not have many components. F itself has just one component. So let's go back to our. Yeah. So f prime, what is going to be the size of the matrix of f double prime? Suppose n is equal to 1. That is, it's just a real valued function of m variables. Then what is going to be the size of the matrix of f double prime?
So it's a m by m matrix. So
Yeah, it's a square matrix, m by m matrix, right? The result that we proved today, what does that tell us about that matrix?
so it's a symmetric matrix.
It's a symmetric matrix, right? And what do you know about symmetric matrices?
So the spectral theorem gives us like an orthonormal eigenbasis.
Yeah, right. So what do you know about all the eigenvalues of this matrix?
They're all real.
They're all real, and in fact, more than that, we have all of them, right? In that you can you can diagonalize this matrix. So this is useful for us, and we were supposed to revise it, and I'm happy to revise it in the course. But if you have done it, then we need not spend a lot of time.
So actually, like in our ALG course this semester, we took like a good 4 to 5 weeks just covering like linear algebra.
Right, linear.
So we actually did spectral theorem just a few weeks ago in the
right
course.
Okay, so yeah. So by the way, so the next thing is we will do Taylor's theorem. So please read the one variable Taylor theorem. Let me write that down. And after that, considering that I have given you homework, so I've given you a fair amount of work, and the midterm is coming up. So I will not start any major topic until I'll not start any major topic for the next 2 or 3 classes. We'll just see a bunch of examples. Maybe we will review linear algebra, and then we can maybe do maxima and minima. The new topics, that is inverse function theorem and implicit function theorem, for that we will wait until after the midterm.
Excuse me, sir.
Yes.
Sir, is it fine to submit handwritten solutions for the homework?
Yes. So that's what I said at the beginning. So for the first 2 homeworks, until the midterm, I don't want to if you want to take, that's perfectly fine. If you submit handwritten solutions, please write a different problem on a different page, and please put those pages in order, so that when the graders are going to correct that, they can have an easier time just locating the solutions. And please label everything clearly, right? And please write everything legibly. Do not scratch out. In general, it is a good idea if if it is going to be a difficult thing, or if it requires some thinking, you first write down your solution in rough, and only when you realize that, okay, I have gotten all parts correct, then you write it out completely. I mean, your goal should be to write a solution that can be published as a model solution, not for somebody to check and find mistakes in, but for somebody to read that and learn from.
Okay, sir.
So just one last thing. Like the drive folder for the notes and the lecture videos has like not been updated in like a really long time. So it's
Right. So yes, somebody pointed out that at the beginning, I think I'm at least 2, maybe 3 lectures behind. So I will do that today itself.
Thank you so much.
Sir?
Yes.
I wanted to ask what the motivation for considering delta was, because I've seen that quantity once or twice before in like very different situations. So I want to know if there's what the motivation here was, and if there's any like sort of meta motivation that
Right. So I got all of that except which quantity did you say?
Delta, sir. Delta FQ.
Right. So delta FQ. But okay, so but you see, this is kind of inherent, right? In that you want to go from, I mean, you somehow want to go from one corner to the other corner of the rectangle, right? Effectively, what are we doing? We are comparing two ways of going from one diagonal of this rectangle to another. One way and the other way.
Right.
Right. So still, I mean, that is a picture, but the quantity itself, I cannot give a better answer rather than saying with the benefit of hindsight, you see.
Okay.
In that this 4 term, if you rearrange the 2 middle terms, then that exactly is that this is the quantity that when divided by h times k, this is the quantity that is allowing you to ask that question precisely. That does changing the order of the limits, first letting h go to 0 and then k go to 0, or the other way around, how does that compare? If you okay, maybe this is the thing, that when you write and so actually good, so maybe this is how I should have started. You see, when you are trying to compare the two partial derivatives, if you just write down the definition, then you have to let both variables vary, you see.
Right.
And so if you write down the definition of D12 and D21, then you see you will be led to consider exactly this quantity. Now that I haven't worked out, but it should not be difficult. So if you just follow your and you know, this is often the case. Many times when you certainly when you write a textbook, or certainly when you write something polished, you have already worked out, and then you write things with the benefit of hindsight. You see this, no? When some lemma is proved, many times it is not even clear why this lemma is being stated, why this lemma is being even formulated in the first place. It is only when you see it in use in the theorem that you realize, oh, this was the reason.
Right. Yeah.
So okay. So I think as an answer to this question, I will put this as another question, which is, if you just try to follow your nose and try to prove the theorem itself, just say that suppose you have a 2 variable function, and suppose D12 and D21 both exist at a point, right? And suppose you want to show that they are equal. Then you will write down 2 limits, correct?
Yeah, and
if you write down those 2 limits, then you will have 2 variables, h and k varying.
Right. Yeah.
And this quantity, I think you will be forced to deal with this quantity.
Okay, I'll check this out, sir.
And so and so this also tells me, because when I prepared this lecture, again I looked at sources and they both had exactly the same thing, so I basically just followed that. But in order to learn something, it is a good idea to not read the proof, maybe just read the statement and say, okay, what is the most simple-minded, what's the most simple-minded approach? The first thing to try is the simplest approach. If the simplest approach does not work, then you go next. But the simplest approach will also at least tell you what the difficulties are. One of the things that I learned from one of my colleagues in earlier on in the US is, often education is giving answers is telling answers to students of questions that they have not learned to ask. Sometimes this is a real disservice.
Yeah, that makes sense.
So,
Yeah.
So just I don't know how helpful this is, but just to put in a thing, whenever we write proofs, it's always sort of we collect all the material that we probably need that we will need in the actual body of the proof, like lemmas and such, and then we do it.
right.
But that is
Yes.
a strangely unintuitive way of if I read that and most books present it in this way.
I agree completely. I agree completely. So,
Yeah.
but you see, when you are writing a book, to make other choices is difficult.
Right. Yeah, that's
Right. Sometimes people do that. So sometimes you see people writing this, that you do this and then you say we are reduced to proving this, and then you prove that. No, so you you do it as a series of reductions.
yes,
Sometimes people do that, but for really complicated proofs, proofs that run into dozens, sometimes hundreds of pages,
yeah.
it's difficult to organize. Okay, anything else? Yeah, so right, I just seen the chat. LaTeX is fine for homework, absolutely. And LaTeX, plain take, whatever version of take, it doesn't matter, because finally it will be a PDF file. So, yeah, but by the way, one thing, please, whatever you give, please make it a PDF file. Okay. So that it is straightforward rather than maybe some Word file or simple text, some text file, or a PNG or whatever. I mean, let's just have a uniform format. Whatever you do, please convert it to a PDF and okay. Anything else? I hope that you're all started working hard at the homework. And remember that I will hold you accountable not just for the problems that I'm collecting, but all of them, including the ones in the lectures. All right. So if there is nothing else, then let's stop and then we will continue on Friday. We will do Taylor's theorem.
Thank you, sir.
All right. Bye, everyone.
Thank you, sir.